4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Hi, everyone. Thanks for tuning in, and thanks to the ASRG for offering us this platform and this time to reach you to talk about code signing and key management and its implications on code signing. Today, we're going to talk a little bit about code signing itself and how it works. And then we'll dive right into some of the use cases for code signing and some of the things that make code signing more effective and are critical in supporting code signing infrastructure. My name is Dan Murdock. I've worked for Irdeto for over 15 years, and I'm the chief architect in Irdeto's Connected Transport Group. I come from an automotive background, having worked for Ford and Visteon both, as well as for Motorola AEG prior to their acquisition by Continental. Irdeto is the world leader in digital platform security. We've been in business for over 50 years protecting and securing digital and previously analog systems before cybersecurity really was a thing. Irdeto is a large company with offices all over the world, including our headquarters in Amsterdam. We have hundreds of customers worldwide and have protected billions of devices as well as billions of licenses and credentials issued at very high availability from our secure operations center and from our cloud services. We're a company of a little over 1,000, and over 70% of our employees are in research and development. We're very much a tech company. We are ISO 9001 and 27001 certified, including our secure keying operations, for example. And we have, over 400 patents and patents pending. And finally, we are the inventor and key patent holder of white box cryptography. The founders of some of our subsidiaries invented that technology. So let's jump right into code signing. What is code signing for Code Signing 101? Code signing is the process of digitally signing software to guarantee and assure the identity of the signer, so of the creator of the code, so authenticity, as well as the integrity of the software at the time that the signature is verified. Very straightforward description. How do you sign code? So code signing is a three-step process. The first and critical step is hashing the entire code space and the entire file to ensure that you've created a cryptographic hash of the entire firmware. So this is typically something like SHA-2 or perhaps SHA if it's a somewhat older target chipset. That hash is then signed by a private key. Again, that's a cryptographic operation using cryptographic credentials. The public key then, together with that signature and the software itself, is packaged into a bundle for distribution and verification on target devices. And that's the basics of code signing in general. Code signing is extremely important in that it ensures that both intentional and unintentional changes in the software are found. So certainly intentional changes, we understand tampering, attackers trying to change software, things like that. But unintentional changes can also be introduced where there are bit errors or omissions in the software introduced just through the nature of moving digital data around. It really does prevent rootkits, tampering, and like I said, transmission errors, and importantly, trust for specific keys and specific signers can be extended or withdrawn based on the operational parameters and nature of the continuing and ongoing operations. However, code signing cannot protect against threats that are introduced before the software was signed. So if you have a bad actor in the software creation process, or after the signed software is verified, whether that's at load via OTA or at load via bootloader, once that's been done, the software can be vulnerable. It doesn't prevent against programming errors or buffer overflows or any things like that, nor does it prevent against runtime manipulation or runtime attacks. And it relies very heavily on the secrecy of the signing keys as well as the integrity of the root of trust itself. And if either is compromised, the guarantee of authenticity is lost. So let's jump right into the standard secure boot use case. So secure boot is really about ensuring as an ECU is executing that the software it's loading and executing has integrity and is intact. Excuse me. So an ECU can run software that controls obviously many different capabilities, braking, steering, radio, lights, lots of features of a vehicle. All of them are controlled by software, and all of this software is loaded in it by an ECU. Depending on the nature of the ECU, software can be easily attacked by hackers, and a compromised ECU can have severe impact on the vehicle's operation and safety. So a secure boot process ensures the whole boot chain is loaded in an authentic and integral way. So if you look at the example on the left, which is a typical example for something like a head unit or an in-vehicle infotainment unit, you'll have a multi-stage bootloader where the primary bootloader is typically immutable and in ROM, so cannot be changed. And it will load the secondary bootloader, which will then load the kernel, which will then load initd and the Linux system itself. So the primary and secondary bootloaders are configured as part of the hardware process. The kernel is then typically loaded and updatable as software would be in a typical software system. Importantly, if you were to look at the contents and the operations of the primary and secondary bootloader, the primary bootloader's responsibility is really to ensure that the secondary bootloader loads intact and that the chip is brought up as configured. So the GPIO is configured in the right way, etc. So the primary bootloader would verify first the hash of the public key and then use the public key and the signature of the secondary bootloader to ensure that the secondary bootloader is intact. The secondary bootloader then does the same thing using the public key and signature of the kernel to load only an authentic kernel that's been signed by the creator. And this is how boot chains all over work now. This is an example for an IVI that has a higher level operating system like Linux running. For a traditional ECU, you may have the same two stages loading a much smaller RTOS ECU firmware instead, but the process is largely the same. So importantly, why does this matter, or what happens when it's not in place? Well, this happens all the time. This is simply an example, but vulnerabilities in vehicles in general, and this is from late 2016, can allow software to be introduced specifically when it is not signed, can much more easily allow software to be introduced through remote connectivity, remote access. Almost all vehicles now have remote access through infotainment, through telematics gateways for intended OEM update and things like that. And excuse me, this vulnerability in particular was through the infotainment unit and Wi-Fi connection, where researchers were able to attack it and gain access to the car's CAN bus. Through that CAN bus, then, an over-the-air update, an unauthenticated over-the-air update was pushed because over-the-air update authentication was not mandatory. And so because that software did not need to be verified, it could have been, but did not need to be, it was allowed to be loaded, and then the researcher then was able to take over key functions of the car. So the typical steps are establish remote communication, escalate your privilege from perhaps some system that's only doing one thing, like loading maps, through an exploit in the high-level kernel to give yourself root access. Allow yourself then to take over as root to drive the OTA system to replace some firmware in the vehicle. And then finally, with that replaced firmware, allow yourself to control some specific actuator, whether it's the wheel or the brakes or the lights or the radio or any other aspect of the vehicle that you could control remotely. So as you can see, this does not take advantage only of software signing or the absence of software signing, but also of many other areas in the system. Those other exploits and vulnerabilities in the system will nearly always be there. And so the reason code signing is so important is because it's nearly impossible to mitigate against all of the potential vulnerabilities in the high-level OS in something like a connected infotainment system. And so because of that, it's critical to ensure that the downstream systems cannot be affected. So domain isolation, for example, is a common way of approaching it, but simply creating walls between those systems isn't necessarily a complete solution, given that those walls can sometimes be broken. So perimeter security is rarely sufficient. And so this distributed security, where each ECU firmware is excuse me, verified as it's run, is critical. This diagram shows how an OTA platform can secure update. The OTA platform itself can be verifying either through the primary or more often a secondary stage of code signing the update package before it's delivered to the vehicle, or within the ECU gateway before it's delivered to the ECU itself. So for ECUs where you have a multi-stage boot, where you have multi-stage bootloaders and code signing, this can provide an additional layer of protection. For ECUs where you don't have any code verification or secure bootloader capabilities, this can provide effectively gateway verification as the ECU is loaded. So at least ensuring that the OTA platform itself can't become a vector for deploying rogue code, because it requires signing before it will load it into the vehicle. So forcing attackers to find another way to bring code into the vehicle. Next, we'll talk more about code signing keys and the lifecycle management that's required to manage them properly. So, excuse me. So code signing, working together with key lifecycle management, is a really important part of overall operational cybersecurity today. Key lifecycle management systems like Irdeto's keys and credentials manage all these cryptographic materials or secrets in embedded devices. So these secrets are critical, and as we talked about, they must remain confidential for their useful lifetime and available for code signing and other secure operations throughout their lifetime. So within the context of code signing, the signing keys are the secure material we're talking about. In the context of, for example, secure debugging or secure communications, signing or potentially encryption keys would also, in fact, be that secure material. So the process for managing the lifecycle of a key is that a key is then is created, and once it's created, it's provisioned to a device and to the cloud or the signing system to allow for signing. Once that's done, the next step in managing its lifecycle will be to renew or update that key at some point. The protocol for the key's use will also include the ability to renew or update that key. Finally, when the key expires or needs to be revoked due to an exposure or vulnerability somewhere in the system, that key is revoked. A new key can be created and then provisioned to replace that revoked key. So this is basic key lifecycle management in general. It's typical to code signing, but typical to many other systems. And so why is this so important? Well, it's critical that these steps are in place such that systems can maintain integrity over their lifetime, because the lifetime of a system is typically far longer than the lifetime of those keys. To do this effectively, operational cybersecurity can be very challenging and sometimes somewhat costly. So to do this effectively, a key lifecycle management system, again, like Irdeto's Keys and Credentials platform, needs to integrate to many different points in an operating environment. Why is key lifecycle management so important? Well, because key lifecycle management is complex and integrates in many different areas of an enterprise, it's critical that it is done in a way that can be trusted, can be integrated with the critical aspects of operation, and can be managed by the teams, administrators, auditors, and analysts who manage that system, and can be live and lively for manufacturing to not delay manufacturing processes. So platforms like Keys and Credentials must be integrated with an OEM's manufacturing processes, as well as an OEM's key lifecycle management backends that having their own. It must be able to manage the credentials and deploy them to fielded ECUs. It must be able to deploy credentials to continuous integration and continuous deployment systems and DevOps systems, specifically for code signing, in fact, in this case. Those systems must be manageable by admins and auditors, as well as developers, such that they can get access to and update the credentials that they need, not only for the security of production credentials, but the availability of development credentials for the developers. External trust authorities and identity providers also need to be able to challenge the system for authentication of specific operations. And 24/7 network operating and security operating centers need to be able to monitor the state of things. And then finally, physical security centers with hosted hardware security modules, such as Irdeto's Ranger Room, for example, which is where we would operate our very stringent ISO 27K operations for key management, including secure facilities that have many 4 eyes operations and 4 eyes procedures, and specific rules about physical access control with an air-gapped network. Can then create and manage those critical system credentials. It's important that a system like this can support multiple keying schemes and key types to support the wide variety of keying and cryptographic needs for a customer like a large OEM. It's important to enable a flexible public key infrastructure and code signing process so that DevOps and development can continue and not be impeded. It's critical that those secure keying operations integrate seamlessly with all the other functions, such that there is no downtime introduced by keying. Most importantly, providing both machine and human interfaces for managing and interacting with these services, such that automated systems and manual operations can be performed. And all of this really is in support of supporting authentication and authorization for specific keys and specific identity providers. So all of these pieces need to come together to create an effective key lifecycle management system to enable code signing and the operational cybersecurity that comes with it. So how does Irdeto's keys and credentials support code signing? So we support it through the creation, provisioning, and management of those keys, as well as the software signing process. So in the diagram on the right here, you can see typical setup steps for a service where you're configuring that service, integrating the driver for that service into the device, and then configuring that device or those devices over time. From a day-to-day operational perspective, keys are created and provisioned, or created and then used in the signing process. And those signing processes and provision processes can be automated in most cases, and manual where there's need to do so, whether it's a specific one-off step that's an unexpected step in the production process, or a step to override perhaps a system that's malfunctioning and needs to be something that needs to be done manually to move past that. Those things can be done manually, but are obviously preferred to be automated over time, in particular in support of both DevOps and production. One final use case we'll talk about is security access. In this case, if you were to look at, for example, UNECE R155, increasing requirements regarding cybersecurity are coming to the automotive space. The implementation of cybersecurity processes and infrastructure to handle cryptographic materials, keys, passwords, and certificates, are the regulations for these systems are sunrising now and will be mandatory in more and more jurisdictions worldwide in the future. A key lifecycle management system is absolutely critical for an ECU supplier in particular who was to implement, or an OEM who was to implement secure debugging capabilities, as an example in their ECUs. ECUs need to protect access to these sensitive commands that allow for the exploration and debugging of the software in the system, as well as the manipulation of that software to identify root causes of field failures, but only allow the access to those for authenticated use by authorized staff. And so when a ECU is created, if you look at this flowchart on the bottom, a diagnostic key, for example, has to be created and paired to the ECU, but it has to be accessible, not only created but also accessible to analysts, engineers, and the like who will be potentially debugging that module in the future. Once that diagnostics key is configured in the system, it needs to be managed for the lifetime of the ECU and available in the event of a field return or worse, a crash where there's NHTSA investigation, for example, and debugging might be legally required. And so granting access to this key is a very important step, but also a very sensitive step. Managing that key and its use is really is a core principle and a core capability of what a key lifecycle management system like Irdeto's keys and credentials can offer. And then, as we discussed earlier, integrating that capability into other systems of an enterprise is really important to make this a seamless procedure and not something that takes days to get started or days of manual operation to execute. So in summary, code signing is a public key infrastructure technology that enables manufacturers and automakers and businesses to certify that communications and software is coming from a trusted and authorized source. It's a critical part of digital infrastructure today, all over, not just in the automotive space. Code signing is critical to attesting the authenticity and integrity of the software, proving its origin, and proving that it has not been tampered with or damaged. And code signing is an important and necessary part of the overall cybersecurity posture of an enterprise or of assets and equipment, but not sufficient without a key lifecycle management system in place backing up code signing. Code signing will surely fail, either from the perspective of not being able to reproduce, to create new signatures, not being able to replace, revoke, and update keys, or not being able to manage those keys over their lifetime. And so code signing is an important but insufficient step in today's society in terms of managing cryptographic posture and secrets. So thank you. Thank you for your attention today. I hope you've enjoyed this presentation, and I'm excited to answer any other questions you have or engage in further discussion. You can reach me at dan.murdock@irdeto.com. You can also find me on LinkedIn as below. Thank you for your time and have a wonderful day.